Section 4.7 is arithmetic or arithmetic sequences. I can identify and extend patterns in sequences, and I can represent arithmetic sequences using function notation. Big ideas here. Some sequences have function rules that can be used to find any term of the sequence. When the pattern in a sequence is identified, the sequence can be extended. So, a sequence is an ordered list of numbers that often form a pattern. Each number in the list is called a term of the sequence. In example 1, we're going to describe a pattern in the sequence and then figure out what the next two terms of each sequence are. So here, to go from 5 to 8, I can add 3. If you're not sure, we can take our second number minus our first number, and that figures out how much our first number was changed by. Here, we added 3. To go from 8 to 11, again, we can add 3. To go from 11 to 14, we can add 3. So here my pattern is that we're always going to add 3 to the number before it. Okay, to find our next two terms, I can continue that pattern. I can add 3 again and get 17. I can add 3 again and I can get 20. So there's my next two terms and my pattern. In B here, I can get from 2.5 to 5 a couple different ways. I can add 2.5, or I can multiply by 2. Again, if you're not sure, take 5 minus 2.5. We get 2.5. That's what our change was from 2.5, a positive 2.5. We added it. Or we can take 5 divided by 2.5, and it gives us 2. And that's what we multiplied here by to get to our new value. Okay, to go from 5 to 10, I can either add 5 or multiply by 2. And since I can't get there by adding the same thing every time, I'm going to get rid of that. My pattern, it looks like, is going to be times 2. To go from 10 to 20, I can also times 2. So yeah, here my pattern is going to be that we multiply by 2 to the number before it. To continue that pattern, I can multiply by 2 and get 40, and keep that pattern going by multiplying by 2 and get 80. Now, feel free to pause here and give this a try if you'd like. We're going to describe a pattern in each sequence and then find the next two terms of each sequence. So here my pattern is how I go from one number to the next. From 5 to 11, I can add 6. 11 to 17, I can add 6, and 17 to 23, I can add 6. So my pattern is going to be every time we add 6 to the number before it. To continue that, I continue my pattern. I keep adding 6, 29, and 35, and that gives me my next two terms of the sequence. In B, to go from 400 to 200, we multiply by a half. We always want to write these as multiplication or addition instead of division and subtraction. So here I take 200 divided by 400, so where I am divided by where I started, and reduce, and we get half. So we multiply by half. The other thing we can do is if we think about this as dividing by 2, we can multiply by 1 over 2. So here, again, I'm multiplying by a half. We could have checked addition and said that we added negative 200, but here we only add negative 100 or subtract 100. So we don't want to go with addition, we want to go with multiplication because we want the pattern to go all the way through. So here, my pattern is multiplying by a half or 0.5. To continue this, I'm going to multiply by a half again, which gives me 25. And I'm going to take that and multiply it by a half, which will give me 12.5, or 25 over 2. Feel free to give C a try. Here our signs alternate. I go from positive to negative, so I know I have to multiply. The only way I can alternate signs like that is if I multiply. I can't add the same number every time or subtract the same number and get different signs every time. So here I'm going to multiply to go from 2 to negative 4 and multiply by negative 2. Negative 4 to 8, I multiply by negative 2. 8 to negative 16, I multiply by negative. And we can check that by taking negative 4 divided by 2, which gives me negative 2. I can take 8 divided by negative 4, and I get negative 2. I can take negative 16 divided by 8, and I get negative 2. So any second number divided by the number before it. Number before it. Number divided by what's before it. And it always gives us that negative 2 that we're looking for. So here my pattern is going to be multiplying by negative 2 to the term before it. And to continue that, if I multiply by negative 2 again, I get a positive 32. Multiply by a negative 2 gives me a negative 64. So here are my values. Go ahead and try D. Here our numbers are getting bigger. So I go negative 15 to negative 11 to negative 7 to negative 3. I'm going to be adding, because I got bigger by the same amount each time, 4. Add 4, add 4. Again, if you're not sure, take where we ended minus where we started. Minus a negative means plus, and it gives me a positive 4. So we add 4. Here, my pattern then is that every time we're going to add 4 to the number before it. To continue that, if I add 4 again, I get 1. If I add 4 again, I get 5. So 1 and 5 are my values there. In an arithmetic sequence, the difference between consecutive terms is constant. So the change between them is constant. This difference is called our common difference. So we add the same number. Sometimes it's a negative number. Sometimes we're subtracting. We write that as adding a negative. But it's always going to be the same. Okay, we're going to have the change between them be constant. The difference between. And that difference is called our common difference. So we're going to tell whether or not the sequence is an arithmetic sequence or an arithmetic sequence. If it is, what's the common difference? So here, from 3 to 8, I add 5. To go from 8 to 13, I add 5. And to go from 13 to 18, I add 5. So here, since I'm adding every time, and it's the same amount every time, this is an arithmetic sequence. So is it? Yep. And what's our common difference? D for common difference. Here it's going to be a positive 5. Let's try B. To go from 6 to 9, I add 3. 9 to 13, I add 4. And 13 to 17, I add 5. So here, we are adding every time, but it's not the same amount. This is still a sequence. It's not just this specific type of sequence, because here we're not adding by the same thing every time. Now feel free to pause here and give this a try. Tell whether the sequence is an arithmetic sequence. If it is, what's our common difference? So to go from 8 to 15, I add 7. To go from 15 to 22, I add 7. And to go from 22 to 30, I add 8. So is this going to be the type of sequence we're looking for? No, because our values aren't the same every time. Not just sometimes, guys. I know we added 7 twice, but it has to be every time. So that plus 8 means it is not. Try B. 7 to 9 is adding 2. 9 to 11, we added 2. 11 plus 2 gives me 13. So here, my change is the same every time. We're adding the same number every time. So yes, and our common difference, it wants to know as well. So D equals a positive 2. If we check C here, to go from 10 to 4, I'm subtracting 6, which is like adding a negative 6. 4 to negative 2, again, we subtracted 6, or added a negative 6. Negative 2 to negative 8, we're getting smaller again, so we're subtracting, and it's 6 again. So here, we are changing by the same thing every time. That change is constant. So yes, it's an arithmetic sequence. D is going to be negative 6. On D here, we're looking to see, again, is this an arithmetic sequence? So we're looking to see if the difference between them is the same every time. So we're looking for adding or subtracting. Here, to go from 2 to negative 2, I got smaller, so I subtract 4. Negative 2 to 2, I got bigger, so I add 4. 2 to negative 2, I subtract 4. So we're not adding the same thing every time. So this is not an arithmetic sequence. We are, however, multiplying by negative 2 each time. And that's going to be another type of sequence that I think we deal with in Chapter 7. That's called geometric. So for now, it's not an arithmetic sequence, but that doesn't mean it's not still a sequence. It's still a sequence, just not the type we're looking for. So don't be confused there. If you see a sequence, things where it's going the same, or you can find the pattern, doesn't necessarily mean it's an arithmetic sequence or an arithmetic sequence. It just means it's another type of sequence. The only way it's this specific type is if we're adding the same number each time, and here we are not. A sequence is a function whose domain is the natural numbers, so 1, 2, 3, 4, and so on, and whose outputs are the terms of the sequence. We can write a sequence using a recursive formula. A recursive formula is a function rule that relates each term of a sequence after the first to the one before it. So there's some example on the bottom of the page 275. So on the bottom of 275, they give us a sequence 7, 11, 15, and 19. And we're going to come up with a recursive formula. When we write our recursive formula, guys, we always have to say where we start. A of 1. This is like the amount of our first term. The number inside is our term number. The A of just tells us that's the amount, the output. Okay, the range. And here our first value is a 7. Then we're going to say the amount of any term. Okay, so the value of any term, number, A of n, is going to be the value of the term before it. So the amount of n minus 1 just means the number before, the term number before. So if n is 10, for example, 10 minus 1 would give me 9, which is the one before 10. And then here we're going to add on our common difference, our change. So here from 7 to 11, we added 4. 11 to 15, we added 4. 15 to 19, we added 4. And this is my recursive formula. A of 1 equals 7. A of n equals A of n minus 1 plus 4. So our framework that we're going to have every time with recursive formula, A of 1 equals our first number, and A of n equals A of n minus 1, which means the value of our any number is going to be the value of the term before it plus our common difference. So here again we put our first term, here common difference. We're going to find a recursive formula and then the value of the 8th term. So first for my recursive formula, remember it's always the value of our first term, and the value of any term is going to be the value of the term before it plus our common difference. So here my first term is 70, and every time my common difference is a positive 7, we add 7. So this right here is everything I need for my recursive formula. To find the 8th term, I'm going to continue that pattern. I'm going to add 7. I'm going to add 7. And I'm going to keep doing this until I get to the 8th term. 1, 2, 3, 4, 5, 6, 7, 8. So the value or the amount of my 8th term is going to be 119. Now feel free to pause here and give this a try. We want to come up with a recursive formula for each sequence and then the 9th term of the sequence. So again, with our recursive formula, it's always the value of our first term, or A of 1, and then the value of any term is the value of the term before it, so how much our term actually is, plus our common difference. Here my first term is 3, that's where I start. And to go from 3 to 9, I add 6. 9 to 15, I add 6, and 15 to 21, I add 6. So my common difference is 6. Here's my recursive formula. To find our 9th term, we just keep adding 6 until we get to our 9th term. So we just keep adding to the one before it. We keep taking our common difference to the term before. So to find our 8th term, for example, we take our 7th term, add 6, and get 45. To find our 9th term, we add 6 and get 51. So the amount or the value of our 9th term is going to be 51. And I will stop here and continue in another video.